This video is intended to show how we can model steel beams with a two-way slab in Adapt Builder. This is going to be done in Builder version 2018 Build 1. And we'll start by using the grid settings here at the bottom of the screen. We're going to go to the grid settings. We're going to set up a 30 by 30 grid, and I'll turn the grid on in display. We'll go up to model, and we're going to add a few columns. So we'll add these columns. We'll do 4 bays in each direction. I'll just select those columns now and copy those over. So using Control C, Control V, we could also use the option under Modify to copy and paste. There's some options here to copy paste. These beams by default, or these columns by default, are concrete. So they're 12 by 12 inch concrete. We could reassign them as steel columns if needed. So we'll go ahead and we're going to now just model in just the default beams. Now these beams again will be concrete beams. So I'm just going to model a line of beams, and I'll copy this down. We'll select beam 1, 2, 3, and 4. Use Control C, Control V. And this is our insertion point here, and I'll do the same in the other direction. So we'll assign our components as concrete, and then we're going to change them after we define the steel members. We use Control C, Control V again, and our insertion point is the second column from the top. So that's our lattice, or our grid of steel members, or what will become steel members in this model. I'll go ahead and turn off the grid, and I'm also going to model a slab on top of these. So this slab will be, we'll say, a 6-inch concrete slab. The material assignment is concrete 1. That default, that's 4,000 psi. And using the snap to endpoint, I'll click on the first point, second point, third, and fourth, and then I'll press enter to close, and I can escape, or right click and exit to escape out of the command. So this is the structure, the model that we're going to analyze. I'll now go ahead and we're going to define the generic sections. So under criteria, we're going to go to the generic material property, and I'm going to add a generic material here that is set to steel. We're going to call this steel _ 1. This is just the default. I'll change the unit weight or the density to 490. We can also change, other properties, modulus, shear modulus, coefficient of thermal expansion, and so on. So I'll add this to my generic materials list and select OK. Under the column design or the wall design, under column design, we're going to select the type manager, and under define section type, I'm going to add 2 sections. The first section we're going to add, I'll go in and I'll just call this a W10 by 45. This will be for the column. And then the second section we're going to use for the beam, we're going to use a W12 by 30. Okay, so we'll call this a W12 by 30. And those are the 2 steel members that we're trying to model in conjunction with the concrete slab. So for the W10 by 45, it's a column. The shape is going to be a generic shape. The material will also be steel 1. That's the generic material that we had previously assigned. And once we select the option for generic shape, the program then switches into a general property mode. So here we're going to define the general properties. And the way these are defined is if we have the true shape of the steel member, we'll have a flange, and we have some out-to-out dimension. So this dimension here, we're going to call this bounding dimension B, and this dimension, the flange, we'll call this bounding dimension A. And then the other properties, area, moments of inertia, polar moment of inertia, and the CGs, these are all based on this particular element that we can find in a manual like AISC shape manual. So for the column, the W10 by 45, the flange width for that particular shape is going to be 8.02 inches. So I'll just say 8.02. The depth of the member, the exact depth of the member is 10.10. So we'll go 10.1. Okay, the area is 13.3 square inches. And then we get into the moments of inertia. And in this case, the moment of inertia, the local axis orientation here this is R and this is S. Okay, so we'll use that as our definition here. And bending about R would be equivalent to the IXX, and then bending about S would be IYY from the AISC manual. We'll go ahead and enter IRR first, and IRR will be 248. ISS will be 53.4 for this shape. Okay, J for this particular shape is 1.51, and then we have CG positive. Again, this is in the R direction. So if we look at our bounding box, again, this is R and this is S. So if we take a centroid here, let's say this is our cardinal point of the axes. We have CG positive in the R would be to this side, CG negative is this side, and then S positive and S negative. And so we'll go ahead and enter those values. Positive in this sense will be 8.02 divided by 2, so 4.01. Negative will be 4.01. For the S dimension, we're going to have 5.05 positive and negative. Okay, so we'll go ahead, and that's stored for the W10 by 45, and I would do the same for the W12 by 30. We'll make this this is going to actually be a beam. It will be generic, and steel 1 is the generic material. Same notation in terms of the local axis for the R and the S directions for the W12 by 30. We'll go ahead and fill in this information for that section. Okay, so we have the same information built for the W12 by 30, and then we have the W10 by 45. We'll go ahead and close that menu, and I'm going to save the model. I'm now going to select all of my beam elements. So I'll turn the slab off. We'll go to Model. We could also do this through Visibility, View Settings, but there's a quick access off-on switch here for visibility. We'll turn the slab off, and I'll go ahead and select all of my beams. And I can window select. You can also use Home and select by type beam, and that would also select these members. So we'll select those. We're going to go to Modify Selection, and under Beam, we're going to modify the actual shape. To do this, we're going to select Design Group, and we'll select this as a 12 by 30. Say OK, and if we double click on that element, the section type you see is 12 by 30. The shape, or the material is set to Steel 1. This is inactive. You have to modify it inside of the section type manager located here. And then we could do the same for the columns. So I'll go and navigate to an elevation view, select the columns, and then back under Modify Selection, we'll select the column. And here I'll go back to Design Group and change this to the 10 by 45. And that list is filtered based on your setting for column or beam inside of the section type manager. So those are now set to a column. We now have our slab, columns, beams. If we go back to our default display, you can see we have our structure set here. And what I'll do now is mesh. This slab has no modifiers, meaning that it has stiffness about 1 axis and 2 axis, and those are the local axis directions for the slab, and therefore it's going to behave similarly in both directions. So if we wanted to modify this to be a one-way slab, then we could assign modifiers to the actual slab. We could go into the slab, create a usage case, and I might call this one-way slab. I'll add a new usage, one-way, and once we add that, then we can modify the stiffness for either of the M11 or 22 bending directions along with the axial stiffness. We're going to maintain this as a two-way slab. So we'll go now to analysis. I'm going to mesh the structure. And similar to concrete beams, the program uses the properties associated with the generic material and its particular material designation. And this gets entered into the global stiffness for the structure. So we will have interaction between the concrete slab and this generic element, similar to interaction between, let's say, a concrete slab and a concrete beam. They're handled in the same in general terms with just different properties, both material-wise and geometrically. So after we mesh this, we can analyze. This only has self-weight. We'll just run it under self-weight. So I'll go to Analyze, Execute, Analysis. I'll do this only for the service load, which is really just the self-weight, and we're going to run the analysis for this slab. Okay, that analysis is done. Once the analysis is done, we can go over here to the result browser and we'll select our load combination, which is service total. Under analysis, I could then go to slab and review, for example, slab stresses, slab actions, and contour form. So we might want to look at the moments about the X, moments about the Y. This is really only the contour results, meaning the slab elements, not the beam elements. We could also review beam elements or beam diagrams. So if we go into the beam option, we can look at actions here, and we might want to review the moment, for example, about S or about Z. In this case, moment about S, if we double click on this beam and we go to the FEM tab, or the let's go to the releases tab, you can see the S axis is here. So bending is really just strong axis bending, or it's bending about this S axis relative to the beam direction, which is the R axis, follows the beam direction. So this moment that you're seeing on screen for the beams is the proportional moment based on the loading that the beam takes relative to its stiffness. So if we go under floor design or even under analysis and turn on the numerical display, this will show us those values at the beams versus the contour values that we showed at the slabs. If we wanted to take a composite look at the beam slab interaction and see, well, what is the moment assuming that there's composite behavior between the two, then we would need to use design sections, and we could always use manual sections or automatic design strips for the model. So if we did this using a manual section, we could go up to floor design here, and I'll create a manual design cut. So let's say we wanted to see what the action was along this path with the slab and the beam acting composite, and we'll create a manual cut. I'll just go ahead and design the cut, and if we now go to the manual design sections for the particular load combination, we can then see the actions related to that particular cut length. So this is going to show us the minimum and maximum value over the cut length. This is just the integrated value, the 101.5, and you can turn off the max and min using this option here. So the value that's there integrated over this full length is 101.5 cubic feet. The same can be done for axial, shear, shear in plane, bending, normal to plane, and so on, torsion. Using this value, you could also design per this moment. So this wouldn't make sense to design reinforcement necessarily, because this is really a steel beam, but you can at least get the actions that are composite to this T section for this particular cut. And if you double click on the cut, you can see the program will actually give a summary of these actions it actually will show the amount of reinforcement, assuming that that member was actually a concrete member that you could reinforce, assuming the properties that we assigned to the generic um, component. So that's how you would create a manual design cut to evaluate a system like this. You could also use design strips to evaluate this, and we have other videos that cover the input and the methods for generating automatic design strips using support lines and splitters. If you have any questions, please feel free to contact support@adaptsoft.com. Thank you.